Yes, thanks you. Thanks for the introduction. Thank you for being there till the end and for talking to something a bit less networking, in fact. And more looking through the lens of P4 as an enabler for any other type of application, and in a way, kind of looping to the first talk this morning with the keynote. And so today we're going to have a look at how we're using P4 to improve the way we're looking at astronomy and how we can make sense of the signal, signal from the sky. And so this work is done in partnership with the SKA Observatory. And as you noticed here, I'm from Australia, so even if I've got a very strong French accent, I'm from Australia, and I've got it's already 3 a.m., nearly 3 a.m. So forgive me if I'm a bit sleepy. So before entering into the details of what we've done, I want to give you a very, very brief overview of what we're talking about in the SKA and why we're doing this kind of research. So the SKA is a Square Kilometer Array Observatory. It's a telescope that is physically in two complementary telescopes. So you've got SKA or MID, which consists of 100 of dishes. And you think about like all these dishes, big dishes looking at the sky, and they're called mid because they're operating on a mid frequency level. And you've got the SKA low, which is tens of thousands of antennas, as the one you see on the on the right there. And these antennas are going to be in Western Australia, and that's going to be the focus of the presentation today. So going back further, astronomers have always tried to look at the sky and try to discover more and more in the skies. And to do that, for a long time, astronomers build bigger and bigger antennas. Problem with building bigger and bigger antennas, it's called gravity. So if you build something that is very, very large, well, then it's very difficult to build it something physically. And you can see the one in Puerto Rico, which just collapsed 6 months ago. So going back to the presentation of today, so we're focusing today on SKA low, which consists of low frequency range, frequency from 50 to 350 megahertz. So you've got up to, on the final change, there will be up to 131,000 antennas spread across like 500 stations. So you can think of a station as a bunch of antennas grouped together, and you put this station in the middle of nowhere in Australia, where there is not too many frequency interference, and you've got a maximum baseline of 65 kilometers. So in the SKA low, the bandwidth is not so much the challenge, but we've got so much data coming from everywhere. So that's where the challenge is. In the SKA, you can see the whole sky simultaneously. And then what you need to do is you need to digitally multi-beam in the sky to steering the narrow view. So you want to focus at some point in the skies. And obviously, the next challenges that we'll see, and that's why it's already in the desert, there will be a lot of interference, whether it's from the satellite, FM, TV and communication, and also some variable ionospheres. So how do we do signal processing based on all these antennas? So as you can imagine, so you've got like all these antennas, then you need to do a digital, analog to digital conversions. Then using these 131,000 antennas, they are divided into a number of apertures looking at the same point of the sky, which is a first level aperture beamformer. So you do a first beamforming of the signal, and then from this first beamform signal that generates 6 terabits per second of data, and it's going into what is called a correlator and beamformer. This correlator and beamformer, what it's doing is that the correlator will form complex visibility between two pairs of apertures. which is basically so power integrated over some timestamp, time period. And you can do also a second level beamforming from the 100 of antenna to get like a higher sensitivity and tight array beams. And so that's what we're talking about, and that's what this is the talk is about, is how do we build this kind of correlator and beamformers. Then from the correlator and beamformers, there's two types of product, broadly speaking. The first type, using the correlated signal, will be sent to what's called a science data product, where it's a supercomputer that will Fourier transform all to the visibility to form images in the skies, very simply speaking. And you've got also beams that are used to time non-pulsars and search for new pulsars or transients. And that's what we're using the beamformer. So you've got 6 terabits of data in, 7 terabits data out to the correlation, 2 terabits of data per second to the pulsar search and timing. And that's what the correlator is capable of producing. So how was it done in the past? So in the past, basically, astronomers and people building radio astronomy instruments, they were using like bespoke custom-made hardware. So this custom-made hardware that you've got an example here, that was a prototype that we built with, we were building with Astron. As you can see, you've got like basically an FPGA card connecting with a few 100 gigs interface at the front. So you've got the input coming from the first aperture signals, then it will have to be treated and routed to the correct FPGA to do the beamforming and the correlations. And as you can see here on the back panel, that's how the data was spread around later on. So in the past, it made more sense to build this custom-made hardware because the astronomer were building a lot of them. Problem is nowadays is this hardware is kind of lagging in the technology because it's evolving very, very fast. And also we don't have, you need to do all the quality assessment and make sure that everything is working properly. So what we're proposing in the atomic cost solutions is to leverage a bit of what the P4 switches are capable of doing. So in the idea of the atomic cost solutions, same as before, you have the coarse filter bank from the analog to digital conversions. Then each station will produce 383 coarse channel. Then the P4 switch in the middle will select the good coarse channel and send it to the appropriate FPGAs that will receive all the coarse channel from all the station and will be able to produce all the output products for one coarse channel. Then atomic and independent, and they become atomic and independent of any others. For the P4 switch, the P4 switch will supposed to receive the signal, then using some data protocol speed or codif that are jumbo frame from 2000 to 8000 bytes, will send the data to the beamformer and to the correlator. So you do multiplication of traffic, do some other zoom mode. It will do the flow health monitoring. It also do facilitate PTP timing for the alveoles for this processing. And it's also interface with the rest of the telescope, doing ARP, potentially RDMA later. And we can see later on if we can do some support for further computations. The second building block of our solution is by using this this off-the-shelf hardware from Xilinx, or it could be Intel, but we're using Xilinx, where they called Alveo. It's a series of FPGA cards where you've got two 100 gig Ethernet coming in, then you've got an FPGA, and you've got 16 gigs of high bandwidth memory attached to the FPGAs. And the goal is to put 20 of these cards that are passively cooled in servers. And this way we can develop in a very standard Linux environment. And since we've got the 100 gigs Ethernet already there, there's no need for NICs and there's no need for PCIe transfers. And as I said, like it's 16 gigs of HBM and 9K of digital signal processing already on board of these FPGAs. So what is these FPGAs doing? So I'm giving you just an example of how to do beamforming, and I'm not going to enter into all the details because otherwise we're here for like another hour, I think. But to make an analogy with what is going on in the networking world, basically the FPGA will do a kind of run to completion, but by doing a lot of batching. So that's why it's like a kind of batch to completion based processing from the data flow and in. So the data will come from the P4 switch. Then it will go to the 100 gig interface. We can decode the headers of the speed packets. Then we're going to store this information into these filter banks HBM memories. Then once data from all these antennas is received, and we've received at least 64 milliseconds of data, then we can just start doing the coarse delays and another filter bank, PST filter bank. So this PST filter bank is like, think about it as an FIR filters and an FFT to split into finer channel. Then we can store this information again into another stage, which is called beamforming HBMs. And then from this end, the beamforming can be probably performed. And it's just, it's summation, the various per station and per beam complex weight that will be applied. And there will be some correction for the ionosphere, etc. and etc. Then we will have formed multiple beams. And I think if I remember correctly, up to 16 beams to point at different direction in the skies. And then we can send this information to another processor in the telescopes. So that's what we do in beamformers. We've got obviously register interface provide like all the control and the monitoring. Everything is in fixed point processing, and the processing output onto the network at the control time using the P4 switch as a PTP boundary clock. So that's all very nice. So now, is it working? So what we've done, we've implemented a first version of the beamformer. The correlator is coming up this year. We've implemented what I've presented just before on the P4 part in an APS-Networks BF6064X-T. We're using a Contel server with 20 U50 Alveo, and this is going to be upgraded to U55. We've got a station emulator and a capture emulator, which are based on a Linux server. And we've got a PST engine that is a production instrument that is going to be used in the SKA. So the idea is we're going to have a model that will generate the input. We send all this data to the P4 switch. The P4 switch sends the correct data to the Alveo server, to the correct Alveo, then back, and that will have formed two beams, and we'll be able to capture these beams and compare the two results. So the way we're going to emulate the pulsar is based on MATLAB models that describe the signal processing as well as generating the input for the data. There's various parameters, and you can have a look at the paper for a bit more details. But basically, we want 64 station, 15 kilometers diameters. We want to embed in the signal two pulsars with the same frequency of 3.32 milliseconds. And the beamformer is going to create these two beams pointing at exactly where the pulsar is. So this is the output of the models. And as you can see, you can see absolutely nothing. Everything is buried in the signal, and you can detect anything. So once it goes through the P4 switch and to the Alveo, the P4 switch will operate as a boundary clock to synchronize the Alveos. From the antennas, it will also respond to ARP request, route the correct channel to the Alveo, and for that we're using the speed protocol, and we are focusing on these three fields in the header. From the beamformer, you want to route the correct beams using the beam number, as it's as simple as it is. You respond to reverse ARP from the science product as well, and you want to generate later on ARP request to help the data center to build this onto topology. What we've also done is we put a bit of telemetry. We've got a flow rate for the channels, the beams, the protocols, and we can detect potential loss from the antennas because all these protocols are just on top of UDP, and so we've got absolutely no idea what's happening, at least from the point of view of the system. So as a result, as I mentioned, we've got like a capture stations, and so that's, we can see there the raw data as produced by the beamforming for the pulsar number 1, and you can see a kind of periodicity there across all the different channels, suggesting that there might be a pulsar. And so that confirms that the beamforming is happening correctly. And to further confirm this hypothesis, we pass that into a state-of-the-art pulsar timing framework for the pulsar 2. And you can see here clearly the fake pulsar, because they will never be that bright, detected, and you can exactly measure the periodicity of all that. And the switch were able to separate the two streams in real time, obviously. So the next step for our validation of all that is to push the switch to the limit. At the moment, we're sending like 40 gigs per second on every port of the switch. We would like to see if we can go to 199.5 would be great. In summary, in this talk, we've introduced like a new approach for radio astronomy, which is called Atomic COTS, which leverage P4 and Alveo architecture, and we can see that it can establish a massive, comfortably establish a massive network-attached accelerator. This architecture is highly scalable, reconfigurable, and cost-efficient, and it can apply not just to astronomy, but also maybe to other signal processing signals, like for 5-6G beamforming, for example. Not so sure, not very sure there, but like there is some kind of similarities there. The P4 switch, and I'm going to focus more on the P4 switch here. The P4 code at the moment is relatively simple, but it provides very important functions, and it's a very the enabler of the solution. Like we can gather the relevant data to the correct Alveo. We've got a transparent multiplication of the traffic for parallel processing. We've got a telemetry, and we can hide all the complexity of the rest of the telescope for the Alveos. In the next step, what we're going to investigate is like, could we support also the science products with inline, for example, like if I'm going back to the pulsar, you can see that it's very periodic. So could we do some kind of inline data folding of this periodicity? For example, could we do some support for machine learning? Like then, literally, the sky is the limit in this case. And as a conclusion, the CSK construction has started, and we will develop the firmware and the software over the coming year to control and monitor all that. So thank you, everyone, and that's it for my presentation.
Was an application of P4 that I haven't seen before. Space. So I questions. I'm gonna kick this off with. You said that you do some data folding, or you'd like to add data folding to the pipeline or to the switch processing. What other data filtering or processing do you think could be offloaded that's currently done in the FPGA?
Look, I think there's. So if I'm coming back to this slide there, at the very beginning, so at the moment the P4 switch is contained into this correlator and beamformer, as you can see. The science data product, the science data processor there is basically a giant supercomputer. So you can imagine that, look, if we put the P4 over there to be tailored to do science data processing that is tailored for astronomy, I think that might be some good opportunity there, like the kind of machine learning approach for the P4. Problem is for the data for the radio astronomy, and I mentioned it briefly when I talk about the beamformer, is you need a lot of data to do some simple things. So if you need like 64 milliseconds of data at 99 gigs per second to make a decision, obviously the current P4 switch will completely explode. Like it will just, you will overflow everything. So maybe the new P4 switch that have got like an FPGA attached to them might bring something very interesting as well, as opposed to just have like just the FPGA at the end, but have also like this kind of buffering in the network to do the folding over a large period of time. To give you an example, the SETI project required 10 seconds of data because you want to go very, very low in frequency. So that's where the issue are, I think, for the radio astronomy.
Well, these are impressive throughput rates that you have to deal with in this on these switches. It sounds like a real challenge.
The challenge is not, for the SK, the challenge is not so much the bandwidth. For other projects, we've got another project called CryoPath. And in this project, the P4 switch is receiving 28 times 99.5 gigs per second, and we need to send that to 32 Alveo cards. So in this case, we're pushing the switch to the limit, clearly.
And timeline for deploying this system in SCA.
So the timeline, the first iteration of the SKA for SKA low, it's supposed to be mid 2023. And we've got another project, like I said, like the CryoPath, where we're using like a very small version of that that is going to be deployed, hopefully, if COVID stop people from deploying anything, mid next year.
That's a short timeline then, coming up soon.
Yeah. And all the code is available. It's free. It's open source. Everything is open source on GitLab.
This is impressive. And what you're working in a heterogeneous environment here with different types of devices. It must be a challenge to have to program them all and using different languages and different abstractions. Is that how do you overcome that? Did you wish you could program everything with P4?
Well, yes and no. Like, I don't think the P4 language is ready yet to go for the beamformer and the correlator. Like, even if hypothetically you could do fixed point arithmetic with P4 language, the crux of the problem is still where are you going to store the data. So you need to optimize exactly where you're going to store the data, sequentially you're going to store the data, and all these kind of things, which might which still give us more flexibility if we stay with VHDL for the FPGA. But in terms of like complexity of the full system for the SKA, there's a big control framework based on this control framework called Tango, for people that might know it, that controlled every little element in the systems. And so, for example, I'm writing at the moment a Tango connector that will be able to just control the P4 switch. So that will be like a very generic control for P4 switch.
All right. Thank you, Guillaume.
My pleasure.
If there are, so Mario has a question. What additions would you like to see to P4 to support SKA, this use case? What's missing?
Look, I think at the moment, from the point of view of the P4, I think it's nearly all there. I think it's more, if we could look, why we picked Xilinx at the end of the day is we didn't have to come up with anything to handle the Ethernet packet and the IP and anything networking there. Everything was ready from the get-go. It was just install this IP from Xilinx, and the card can decode all that for you. So that's already, you just gain like 1 year of programming the FPGA, as you can imagine. If in the next iteration of the P4 switches with the FPGA attached to them with like 400 gigs between the Tofino ASICs and the Intel FPGAs, if all that was already there as well and manageable by P4, that would be fantastic. That would be amazing. That would be amazing. But I'm not sure if it's there yet.